In the name of Allah, the Compassionate and the Merciful. Hello guys, my name is Salar Delavar Qashqai. In this video, we're going to talk about the ductility damage index based seismic assignment of this steel concrete composite single span plate girder bridge superstructures. You see guys, in here we have one single span simply supported composite bridge in here with this section. So in here we have 5 I section and with defined concrete properties at the top of this bridge, and we're going to model it with OpenSys with just 2-dimensional modeling and with defining as a simple 2D beam section and defining 101 nodes and 303 degree of freedom. And for evaluating the response spectrum of this analysis and outputting the different damage index, we're going to run 60 steps changing the mass and then finding our outputted data. So you see guys, in here for steel rebar and also plate, we define these strain and stress relations, and also for confined section we define these Mander relations, and also we are going to change the period of the structures. We defined the elastic lateral stiffness and then finding the mass, and in each step we are going to change the period of the structures, and then with this mass we're going to run the analysis, push over analysis, and then nonlinear dynamic analysis. So at the end we're going to evaluate the different ductility damage index. First of all, for evaluating the steel rebar or even plate fibers or even concrete fibers, we're going to, for example, for evaluating these fibers of the steel plate and also concrete or even rebars coordinates, strain stress, we're going to output the analysis report and then evaluating the actual ductility damage index. In here, for example, demand strains comes from nonlinear dynamic analysis outputted data, and also yield strain and ultimate strains comes from simple formula as inputted data of our steel rebar or even concrete or even plate strain and stress relations. And for defining the section ductility damage index, we're going to run the moment curvature analysis for evaluating the yield curvature and also ultimate curvature, and by running the nonlinear dynamic analysis we're going to output the demand curvatures of this section. So and also for running the total damage index of these structures, we're going to run the pushover analysis to evaluating the yield displacement and ultimate displacement, and also running the nonlinear dynamic analysis for evaluating the demand displacement. So you see guys, in here we are going to run three types of analysis: moment curvature analysis, pushover analysis, and then nonlinear dynamic analysis. So we're going to applying the seismic acceleration as a y direction and also incremental displacement as a y direction. After running in each step of moment curvature analysis, pushover analysis, and nonlinear dynamic analysis, we're going to see the outputted data such as ductility ratios, tangent flexural rigidity, plastic flexural rigidity, overstrain factors for moment curvature analysis of the sections, and also running the pushover analysis outputted data for seeing the ductility ratios, overstrain factors, or even plastic flexural rigidity. So you see guys, in here this blue line comes from pushover analysis and the green line comes from nonlinear dynamic analysis. And you see, based on this demand displacement and ultimate and yield displacement, we are going to evaluate the structural ductility damage index and so on. So we are going to plot it, the composite section bridge in OpenSys library. As you see in here, we have 7 rebar layers and defining the I section properties you see in here. So we are going to output the rebar coordinates as strain and stress relations for these coordinates, and also this and this for concrete strain and stress relations outputted data, and also outputting the FOB and butt plate thickness of these strain and stress relations for our outputted data for evaluating the actual ductility damage index. So after 60 incrementation of the mass and calculating the different properties such as displacement, velocity, acceleration, and different damage index of our outputted data, you see in here the displacement has this shape, velocity has this shape, and also acceleration of these structures based on near 0 until 0.5 has this shape. And also for evaluating the displacement, acceleration, and velocity based on neutral frequency, you see has this shape. And for evaluating the actual ductility damage index of 3 fibers of the concrete, so as I told you before, this fiber, and also this fiber for concrete, after 60 analysis of the nonlinear dynamic analysis, you see it has this shape for different fibers, and also evaluating the concrete actual ductility damage index, it shows the negative value. So it shows that the based on this period and until this period we have a very good safety index of our analysis outputted data, and also for steel rebar ductility damage index of, as I told you, these fibers, these and also these fibers. We're going to see the outputted data for strain outputted data and also ductility damage index outputted data for different periods, and also steel plate strain for this fiber and also this fiber. We're going to evaluate the actual ductility damage index. So it shows that the negative value, so it shows that it's very good safety index. But if we change the mass and changing the period of the structure, so the bottom plate, it's going to be going to be yield strain, and so we must take care of these structures for evaluating the actual ductility damage index. So, and you see in here we are going to see the structural ductility damage index based on the period. It has this shape, and also section ductility damage index, it has this shape, and also structural overstrain factor, it has this shape. So we are going to evaluate the 60 nodes with the polynomial regression with good R-squared fitted data you see in here. And let's see the other outputted data, such as structural ductility ratios. Shows that the good R-squared for fitting the data and predicting the next value, and also elastic flexural rigidity, and let's see the other outputted data, such as yield displacement. You see guys in here, so it has U shape, and based on this polynomial regression we can with a good R-squared we can predict the next value. And also you see guys in here, yield based shear of structures, U shape of the structures outputted data, and let's see the other ultimate base shear. It has this shape, and also relations between base shear dynamic divided to the pushover analysis for base shear and displacement. It shows the linear relations with this polynomial regression with good R-squared, and also for evaluating this seismic response spectrum and acceleration response spectrum, it has this shape. So we use these polynomial regressions with good R-squared for predicting the next if the displacements goes to be changed. So with this formula we can find the good fitted data, and also the relations between displacement response spectrum and velocity you see in here. And also we're going to plot the 3D relations between velocity, displacement, and accelerations. And we see in here relations between actual ductility damage index and structural ductility damage index. You see that guys, it has this shape. So we use these polynomial regressions with a good R-squared for predicting the next value. And also actual ductility damage index and structural ductility damage index response spectrum for steel rebars. it has this shape. So you can change it with your own to evaluating different damage index properties of different fiber layers of these structures. The code is available in GitHub, and you see in here acceleration and structural ducted damage index, and also you see in here I plotted the actual diagram of this structure. So this structure has 101 nodes. So actual forces for based on pushover analysis, it has this shape, and also based on dynamic analysis, actual diagram has this shape, and also shear diagram based on pushover and dynamic analysis has this shape you see in here. And let's see the moment diagram based on last outputted data. So based on last outputted data, moment diagram of the pushover and dynamic analysis has this shape. And if we want to find the relations between our outputted data, for example, for evaluating the relations between velocity, accelerations, displacement, and different ductility damage index for our outputted data, you see in here we use the correlations matrix, and you see it shows that most of the data has a good correlated. So for evaluating and finding the best linear relations between them, we must omit most of this data and then run it again for using these properties for multiply regressions to finding best linear relations for our outputted data. You see in here we use these data for evaluating the multiply regression. So it shows that most of them has upper than 5% p-value. So we must work it on it and find the best relations, linear relations between them. And then I also run the lasso regressions for simple modeling for evaluating the structural ductility damage index response spectrum for prediction, and it shows that the R squared is equals to this value. So you can change it with your own data and finding the other outputted values data. And at the end we're going to run the machine learning short-term memory LSTM method for predicting the next value of the section ductility damage index and also the structural ductility damage index. So we're going to define the x coordinate of this section ductility damage index, and based on LSTM method we're going to predict this y as a structural ductility damage index properties. You see that, guys, in here. So if we run it with 1000 iterations, it shows that we get the very good solutions based on this machine learning method. So let's see the OpenSys file of our analysis outputted data. You see in here I defined functions for plotting the shape of the structures, some papers for reading the outputted data, for defining the superstructures, composite bridge, and designing and analyzing the outputted data. Very good books for reading it. I recommend it for reading these books. And also I defined functions for outputting and plotting the data. this code's available in my GitHub, and you can download it and change it with your own. So let's see. I defined the plotted sections based on this library. We can plot the different we can define and plot the different properties in OpenSys, and it's very efficient. I recommend you guys to use this library as a OpsViz. You see guys, in here I defined different concrete and steel properties for confined sections, and also plate and rebar material properties, and defining the different properties, fibers, and then in here we are going to plot it and running the moment curvature analysis of these composite sections, pushover analysis, and outputting the displacement and base shear, and also curvature of this defined nodes as element 50 you see in here, and also running the dynamic analysis and outputting the displacement, velocity, accelerations, and also base shear and curvature of these structures, and defining the length of this simply supported single span beam structures you see in here. So it has 30,000 millimeters with the sidewalk defined sections and also different properties, and you can change it with your own, and defining the rebar diameters for sidewalk, deck, and box. So in each concrete box section we can define different steel rebar properties. You can change it with your own and then run it again, and then defining to plot the nodes of the structures. Example you see in here, you can see as a 3D each nodes, and also seeing the section properties of defined section. This library which I told you is very efficient for defining and seeing your errors in definition of the section properties. Most of the time we are going to define the wrong way of this section properties, so this library helps us to better modeling of the section properties and also plotting it. And you see in here we are going to run the moment curvature analysis based on these ductility ratios which I defined for our model, and we are going to run the moment curvature analysis just one time, because nothing is going to be changed during the analysis of these 60 steps. So and then you see in here we're going to run it and outputting the data, and also in here you see I defined the maximum pushover incremental displacement as a negative 150 millimeters, and defining the nodes as a 50 to applying the incremental displacement, and defining the structural lateral elastic stiffness. And you see in here, after 60 iterations, we're going to evaluate the pushover and dynamic analysis, and by changing the period of the structures. So I defined T maximum as a maximum period, and based on these 60 iterations, you see the mass is going to be changed. So the mass is going divided to the 101 nodes. So we're going to with this PA call or PA call W, we're going to define the each mass and weight of the each nodes, and in here we're going to run the pushover analysis and dynamic analysis, then outputting the real period of the structures. And you see in here after 26 hours, you see the analysis is going to be stopped, and then we're going to evaluate our outputted data. This code's available in my GitHub. You see in here you can change it the order and see the different shape of the linear relations between these parameters, or even polynomial relations between the parameters. And let's see, yeah, at the end we run the loss regression and also machine learning as a LSTM method for predicting the next value with 1000 iterations and look back 40, and you can change it with your own data and run it again. So in the second analysis, we are going to evaluate the sensitivity analysis of this simply supported single span composite bridge, and we're going to define the rebar of this fiber between minimum and maximum, and also changing the I section height from minimum to maximum with running 50 steps. We're going to evaluate the different periods and different ductility damage index of these structures. All the process is the same as I told you before, but in here we're going to change these fibers and also height of these I sections properties between minimum and maximum with 50 steps, and then seeing the results. So it's so efficient, much more than optimization problem. You see guys in here, for example, you want to design this kind of structures and you don't know which one is the very good efficiency for evaluating, for example, in here the damage index of the structures. So I recommend you use the sensitivity analysis. It is just for educational purpose, and I recommend you, if you want to do something like this, do the sensitivity analysis. So you see, by changing the rebar diameters and also height of the I sections, you see we can see the periods go change from 0.23 until 28 for our outputted data, and also this, you see different displacement shape, velocity and acceleration, and also base shear shape of the structures going to be shown in here based on period and neutral frequency. And you see in here different concrete and steel rebar and plate strain properties you see in here, and different damage index for these fibers material properties going to be shown in here. All of them is the negative value, so it shows that it's very good safety index based on these periods. And you see, let's see the other outputted data such as structural ductility damage index, and also by changing the rebar diameters for deck and structural ductility damage index, it has this shape. And also for evaluating the I section height and structural ductility damage index, it has this shape. So if we increase the I shape section height, so the damage index is going to be down. It shows that it's, and also by changing the rebar diameters for this concrete deck, so the structural ductility damage index goes down. And also let's see the other outputted data. The structural ductility damage index based on this period, it shows that these relations, and also relations between section ductility damage index based on this polynomial regression, it has very good fitted shape data. And let's see the other outputted data such as overstrain factors, ductility ratios, and also elastic flexural rigidity, plastic flexural rigidity you see in here. And this code's available in my GitHub. Yield displacement, yield base shear, ultimate displacement, and ultimate base shear. It has this shape. And let's see relations between section overstrain factors with the different periods by changing the rebar diameters and I section height. It has this shape. So with using this polynomial regression, with a good R squared, we can predict the next value. And then you see in here the section ductility ratios with defined with different periods. It has this shape. So with this polynomial regression with a good R squared, so you can predict the next value. And also elastic flexural rigidity, plastic flexural rigidity, and so on outputted data. You can use this method for predicting the next values of this displacement or damage index comes from these structures. So you see yield base shear of the, let's see in here, yeah, yield base shear, and you see it has this shape and very good R squared. You can predict the next value. Let's see the other outputted data. Yeah, in here we're going to plot the relations between rebar diameters changing and height changing of the I sections, and with the relations between the PGA as a peak ground accelerations. So it shows that it has this shape, and also for velocity. So it is the sensitivity analysis of these parameters, and also by changing the height and rebar diameters and displacement. So PGD is going to be changed like this shape, and also relations between acceleration, velocity, and displacement. For all process it has this shape. So in some cases, like in here, we have very different nodes, very higher, and so you can working on it to find the best good fitted data. And then let's see the structural ductility damage index and axial ductility damage index for concrete fiber 1 as a FOB concrete layers of this composite section, and also steel rebar number 1 as a FOB concrete steel rebar as a sidewalk. And let's see the other properties in here. So it shows that the steel plate number 1, it shows that the top I sections fiber plate for our outputting the strain and stress for our structures sections, and then outputting the axial ductility damage index. It has relations between structural ductility damage index and axial ductility damage index. It shows the very good fitted linear relations. So, and you see in here, and let's see the other outputted data. Relations between velocity and structural ductility damage index, it has this shape. So with this polynomial regression, it has very good fitted data. And let's see relations between axial acceleration response spectrum of the structures and structural ductility damage index. It has this shape with the good squared fit data. And in here you see the last base shear and displacement outputted data of pushover analysis and dynamic analysis. So you see in here. And you see we're going to plot the axial and shear and moment diagram for pushover and dynamic analysis of the last data outputted, and then finding the colorations of the each outputted parameters. It shows the most of them has very good correlated. So for finding the linear relations between them with using multiplier regression, we must omit some of them for changing the parameters. For example, changing this, omitting these parameters, then run it again for better finding the best correlations between them. You see in here, for example, in these parameters we have very high p-values, so we must change it and then run it again, and then use the lasso regression for our model for predicting then the values. You see we use the structural ductility damage index. You see with this not good R squared, the lasso regression is going to be fitted data, so it is not recommended for using this lasso regression in our model. So the polynomial regression is much better than others. And let's see in here, we use the machine learning as a LSTM method for predicting the section ductility damage index and structural ductility damage index. So with the 5,000 iterations we get this point. So it shows that the LSTM method for this method is not good for our modeling. So I recommended polynomial regression for our modeling predictions for our different ductility damage index. So polynomial multiplier regression is very efficient. And in the sensitivity analysis Python code, all the process is the same, but in here we're going to define the minimum and maximum for rebar diameters for deck, and you see in here, sorry, it must be this value. And for minimum and maximum I section height is going to define it in here, and then we're going to run it with the 50 steps with the maximum period 0.25 and defining the elastic stiffness defined it in here. So we're going to define just the mass and weight of each node one time, and then changing the rebar diameters and also I section height, and then run it 50 times, then outputting the data. And I told you that how you're going to output the data. So it takes 28 hours, I think, for running the analysis. So it takes so much time, and you see the our outputted data, which I told you before. So in the third file, we're going to do the incremental dynamic analysis by changing the amplified factors of the accelerations of our defined accelerations time history, and then outputting the data. All process is the same as response spectrum and sensitivity analysis, which I told you before. So we're going to change this amplified factors, the values near 0 until 2, and then outputting the data. So it shows the structural ductility damage index based on different accelerations factors. You see in here. Different ductility damage index. It shows these constant values, and also by changing the section ductility damage index and acceleration gravities, it shows it has this shape. With this polynomial regression, it has very good fitted data. And these videos which I prepared just for educational purpose, so you can change the data with your own, and my target is to just learn you how to model and then trying to output the data, nothing more than this. And you see in here structural overstrain factors and acceleration gravity amplified factors. It has this shape, and also you see different parameters for elastic fracture rigidity, plastic fracture rigidity. So, and also relations between displacement, base shear, dynamic divided to the pushover analysis. It has this good fitted linear relations, and also displacement and acceleration. It has this shape. So you see guys in here, we just change the amplified factors of our model, and then with the some running the steps, I think 50 or 60 steps, we're going to output the data. I will show you in my OpenSys file. And structural ductility damage index and displacement, it has very good linear relations, and also the structural ductility damage index and velocity, accelerations, and so on. And you see in here relations between displacement and base shear based on the last outputted data. It has this shape, so the green line is a dynamic analysis and the blue line is a pushover analysis. So based on this analysis, we're going to output the structural ductility damage index. So the negative value, it shows that we are in the safety index. So if the green lines comes from, for example, this position, so the ductility damage index, structural ductility damage index goes to be damaged in some percent, for example 10% or more than. So let's see the other outputted data, such as actual base shear and moment diagram for pushover and dynamic analysis, and also plotting the correlations between all outputted data, and also we use the multiplier regressions for predicting the next outputted value data. You see in here, so it shows in here, let's see, in some cases we have very good correlated data. So for finding the linear relations, we must omit some of them and then try to find the good fitted data. You see in here, so the p-value in some cases like this, and like this, and so we must omit these parameters, then run it again. And we use also lasso regression for predicting the structural ductility damage index. So it is not very good R-squared, so lasso in this analysis is not very good efficient method for predicting the value. And also we use the LSTM method as a long short-term memory method for predicting the relations between section ductility damage index and structural ductility damage index with 50 iterations, and it shows that this method is not efficient for our predictions modeling of our analysis. So let's see the OpenSys of incremental dynamic analysis of this steel concrete composite plate girder bridge. All process is the same, and you see, let's see, yeah, yes, in here with definition of I, we are going to change the accelerations factors. The value is starts near 0 until 2. So with 50 iterations, we're going to run the outputting the data and seeing if the acceleration of the analysis is going to be changed from values near 0 until 2. So the damage index is going to be changed. So then finding relations between all the parameters. So and let's see. So in this analysis, it takes 25 hours for running, and all processes is the same for outputting the data you see in here. And we are going to plot the velocity, acceleration, and response spectrum. and then you can change the order and to finding the best care fitted data. Yeah, and at the end I run the LSTM method and loss regression. You see in here with the 5,000 iterations. You see in here we can find the efficient method for better predicting the values. Yeah. So in fourth analysis we are going to have an movable displacement analysis of this composite bridge. So we are going to move the displacement from this point, and this point, and also at the end this point with the defined 21 nodes, and then running the pushover analysis with the defining the maximum displacement, then evaluating the different strain and stress, and also other factors such as overstrain factors, ductility ratios, flexural rigidity, and so on parameters during the analysis. So all the process is the same, but in here we define just 21 nodes for our analysis with 63 degree of freedom and changing the displacement at each node. So you see in here, if we displacement of the structures starts from this point until this point, so in node 1, which I told you, for example, in node 1, base shear is going to be changed like this, and also node 2, it means that the node 21. So if the displacements change, for example, from here until here, so the base reaction of this point as a node 21, so it changed like this. And also let's see the other outputted data such as concrete strain for different layers. It has this shape, and also steel rebar for 5, it has this shape, and also bridge steel plate strain, it has this shape. So let's see the other outputted data for this movable displacement. Overstrain factor, it has this shape. So you see we have critical conditions in here and in here. So, and you see in here structural ductility ratios. So we have critical conditions in here, and the minimum value is in here. So, and by changing the displacement and seeing the elastic flexural rigidities, it shows that in here and in here we have a critical conditions, and also for plastic flexural rigidity. And you see in here for evaluating the yield displacement, so critical value is in here, and also base yield base shear, the critical value is in here, and also ultimate displacement critical value is in here. And let's see the other outputted data, the critical values in here for ultimate base shear. And you see in here last outputted base shear displacement relations for these outputted data. You can see. So the movable displacement is very efficient by changing in moving loads for evaluating the critical conditions which is going to be happen in this kind of structures such as bridge. So I recommend you do the movable displacements by changing the movable loads. So this method is very efficient for finding the critical conditions of the collapse of the structures during the critical conditions, in uncertainty conditions. Let's see the OpenSys file of this movable displacement. So all process is the same, but in here we're going to define the nodes as 21 nodes, and then defining the maximum period and defining the mass, and at the end weight of the structures, then running the pushover analysis, and then outputting the data. So you see guys in here, it takes I think near 2 hours for our outputting the data, then trying to plot the data for our outputted data. So yeah, you can see and change with your own data. And that's all for this movable displacement. Let's see the other output analysis data. So at the end, in the fifth analysis, we're going to have an optimization problem for our ductility damage index properties. So we run 8 kind of optimization algorithms method. First of all, Newton-Raphson method. The second is genetic algorithm, Firefly algorithm, ant colony algorithm, artificial bee colony algorithm, particle swarm algorithm method, differential evaluation algorithm method, and all at the end artificial neural network algorithm method. So let's see the codes of the algorithm method. I didn't run all algorithms, so you can run it and find any bugs of these algorithm methods and change it with your own. So all the methods near together. So in here we are going to define the section properties, moment curvature properties, pushover, and nonlinear dynamic analysis properties, as same as other files which I told you before. So at the first analysis which I told you, we used the Newton-Raphson method. So our target to find the optimum eye section height of this analysis with the target damage index as a 0.05. So damage index target is a 5%. So with this efficient method we can find the best eye section height of this plate height of this analysis. And you see it takes so much time, so I didn't run at the complete method. So You can run it and find any bugs, or even change it with your own data. And also genetic algorithm, I defined it, and you see process is the same for defining the pushover and dynamic analysis, for outputting the damage index, and then based on this genetic algorithm, and so on. So I defined 8 different optimizations algorithms for calculating the best damage index fitted analysis. So you see, I didn't run most of them because it takes so much time. So but the code is available in my GitHub, and you can change it with your own. And if you have any question, you can have a comment, or even emailed me, and to trying to get it much better for our next videos in my YouTube channel. Please have a comment and tell me know about this kind of modeling. These videos which I prepared is just for educational purpose. Please have a comment and tell me know about this kind of modeling. God bless you guys. Bye.